In this video, I'm going to walk through what I learned in Lesson 11 of the FASTAI course, Part 2. And it's been a minute since I've worked on this coursework and back on it and really excited. And I've also have a blog post version of this that I'm calling The Evolution of Matrix Multiplication. Obviously, it's not a historical storyline, but it's certainly an evolution in terms of making it faster and more optimized the deeper we go into the exercise. So let's jump in. We're going to start by loading up our MNIST data. So I'm mainly going to skip that other than just showing that we have 28 by 28 pixels and we have our images. So we're also going to have some random weights that in a neural net we would learn during training. And because we have 784 pixels, which is 28 by 28, we have 784 weights, and then we have 10 output features. So in the applied sense, this would correspond to 10 digits, 0 through 9. But in this notebook, it's just a bunch of random numbers for now. And we're going to take the first 5 validation set images, that's M1, and we're going to call our weights M2, and these are 2 tensors. So we have a 5 by 784, and then we have a 784 by 10 tensor. In total, we are going to have 39,200 operations that we're going to see in a second when we do a for loop. We grab the shape of M1, that we're going to call A. So A rows and A columns. And then M2 is B, so B rows and B columns. So here are those shapes. And then we're going to prepare an output tensor, the resultant tensor of our matrix product, that we're calling T1. And it's going to have 5 rows, 1 for each image, and 10 columns, 1 for each output feature. So that's the setup of data. So our first implementation is a nested set of for loops. We're going to iterate over the 5 images, then we're going to iterate over the 10 features, and then we're going to go element by element across the 784 weights, as well as across the 784 pixels, and we're going to multiply the corresponding elements in our input and our weights, and we're going to accumulate that sum, that dot product, and it's going to be the first row, first column, second row, first column, etc. So this is something that I've seen before, but for whatever reason it doesn't make sense to me, even though I look at it and I look at ij, and then here's ik, and here's kj. So before I went any further, I annotated this situation so that I can see it, and now I can see it visually. Now it makes sense. So I'm going to walk through my illustration here that I really like. And again, Excalidraw is what I'm using, so highly recommend that for illustrations. So I have my images A. I've got 5 images represented by these 5 horizontal rectangles, and then each item in my matrix A is 1 pixel, and I have 784, which is not to scale. Then I have my weights. I have 1 weight for every pixel for every feature that I'm trying to transform these inputs into. So I have 10 features and I have 784 rows. And the outputs, we're going to have 5 rows and we're going to have 10 features per row. So let's look at how our loop kind of unrolls into this schematic. So we have for I in range AR. So AR is 5. So for each row, we're going to then go for j in range BC. So we're going to take the first column, then the second one, then the third one, all the way to the 10th one. And then we're going to go for k in range AC, and that's 784. So in the first iteration of this loop, we're on the first row here, or first image. And the first iteration of this loop, we're on the first column. And then we go through all 784 elements. And what do? We multiply them together, and then we add them up. We multiply them together, add them up. So we take the dot product, and the final result is the first element in our output. And then we're still on the first image. We go second feature, and then that would be this one. Third feature, fourth feature, so on and so forth until we have our 10th feature. Then we're going to go to the second row, go through each column, and then we'll populate the outputs here. So this visualization makes sense to me. I won't forget it now, and even if I do, I'll just pop back in here and look at it. So that's the naive implementation, and this is what it should look like. So negative 10.94, negative 0.68, and we have 5 rows and 10 columns, just like we have in our illustration. Okay, so let's wrap that into a function, and let's time it, and I'll run this again just to see. Yeah, so it's about 1 second. So if we had, this is for 5 images, and it takes 1 second to do 1 matrix multiplication. We have 50,000 images, so it would take, at least 10,000 seconds or thereabouts to do the matrix multiplication for all 50,000 images. Many matrix multiplications, many such matrix multiplications when we're doing a forward pass of even a simple neural net over a training loop. Obviously, this is not feasible. So what do? So the first thing we do is we are going to try to minimize the number of for loops that we're dealing with. So what we're going to do is we're going to import njit from Numba, and we're going to create a dot product function. And what it's going to do is that it's going to run through this vector A, and it's going to go through the length of A, and it's going to accumulate the dot product starting at 0 between the ith element of A and the ith element of B. It's going to finish that dot product, and then it's going to return the dot product at the end. So if we look at some of these here, so here's an array here, 1, 2, 3, and 2, 3, 4. The first time it takes 1.5 seconds, but then we run it again, and now it's in the microseconds. So this is looking promising. So what do? We update our mapmul function, and this is why I love working in Jupyter Notebooks, because we can progressively update our functions throughout the evolution of our understanding and implementation of our different optimizations. Everything about the data stays the same. We're going to have our torch zeros output matrix. The first 2 loops stay the same, so we're still going over each image and we're going over each feature, except now the dot product between the image row and the feature column is being done in a Numba compiled way. So we're going to convert our tensors to NumPy arrays. We're going to make sure that we get the same result as our naive method, which we do. And now we're going to run this, and we're going to see that we're at about 600 microseconds. So this was what I had earlier run. My Python for loops took 1.09 seconds, and this was 555 microseconds. So this was a 2000 speed up. And just to make sure that I'm looking at that right, 1.09 seconds to microseconds. So that is indeed a very large number. And we divide it by 555, and we get about 2000. All right, that's great. So we have a 2000x speed up. All we did is we put one of the for loops inside of Numba, and we kept the other two the same. So just that alone is really awesome. We can also do that in Python. So here I have matmul again. The data prep is the same, and the dot product is the same, except now I'm taking the ith column, or sorry, ith row and jth column for A and B respectively. I'm doing an element-wise multiplication, and then I'm taking the sum. So that's my dot product. Always checking that we get the right answer. And this takes about 1.64 milliseconds. So if we go 1.64 milliseconds to microseconds, so 1,640 microseconds. So it's about 3 times as slow, or 3 times slower than our Numba compiled, but still, 600-700 times faster than doing 3 loops. We can also do the same with PyTorch. Everything else stays the same, except now the dot product between our pixels and our weights is done with torch dot dot. We get the right answer, and it's a little bit less, right? 20% or so faster. So at each step, I want to make sure I'm visualizing what's going on so I can solidify my understanding of it. So we're still dealing with matrix A, where each row is an image, and we have 784 pixels, except now we iterate across the rows and across the features, and for every image and feature combination, we take the dot product. So we take the product of each corresponding element, and then we add them up, and that gets stored in our output matrix. So here's the ith row of A, here's the jth column of B, and here's the I comma j value of our output. So this is our dot product approach. All right, now we enter the realm of broadcasting, which we learn in lesson 11 came from this very obscure language called Yorick. And broadcasting is basically a way to expand a smaller matrix to match the size of a larger matrix. And that's not necessarily the case. You can, broadcasting still technically works even if you have 2 matrices of the same size, but its true effectiveness comes from when you have one matrix that has a larger shape and one matrix that has a smaller shape, and you're broadcasting the small matrix or vector across the large matrix, and you're performing element-wise operations much faster because you don't have to iterate. You're just making these virtual copies of the smaller matrix across the larger matrix. So easiest to look at it to understand what's going on. So I'm going to take my first image, and let's just make sure we remember that, 5 images, 784 pixels each. And the rule for broadcasting is that we start with the trailing dimension, and if the trailing dimension is 1 or equal to this final dimension, then we can broadcast this up here. So that's why we need to add a unit axis at the end of this, because 784 cannot be broadcasted across 10, but 1 can. So we're going to run this, and this comma none dimension is adding a unit axis in that position. So it's adding the unit axis after the 784. If we look at M2 and M1 broadcast, I guess it's not broadcasted yet, but 1 expanded, not even expanded, what is this, M1 with a unit axis. Now we can broadcast this 784 by 1 across the 784 by 10. So when I do this element-wise operation, what's happening is that this 784 by 1 vector is getting copied over all 10 of these features, all 10 of these 784 values, and an element-wise operation is taking place. So we end up with 784 by 10, but these values now are different than the 784 by 10 we started, because we copied over each of those 10 columns, this vector, and we did element-wise multiplication. So we'll look at a smaller example, but here's M1. M1 has 5 rows, which are these 5 here, and it has 784 values, which are truncated here. So let's start with let's do a smaller example. So let's say we had 5 images, and let's say these images were 2 by 2. So we have 4 pixels. So we have just random numbers here. We have 5 images, and then we have 4 pixels. These values are nonsensical because we would have float values for the image, but let's assume that we have integers for now. So I'm going to grab the first row, which is this one here, and then I'm going to take all values in the column, and then I'm going to add a unit axis. So I don't think I'm going to be able to preserve these values. I should have set the seed, but let's go ahead and just run this. So we have our first row. Now we've added a unit axis. So you can see that each value is now encapsulated in these brackets. So if we look at the shapes, the A matrix full has 5 images, 4 pixels per image. My modified first image with a unit axis has 4 pixels and 1 unit axis. All right, so keep this in mind and we'll refer back to it. Now let's say we have our weights, and I'm going to use the same 1 through 5 integers. I'm going to have 4 weights, each corresponding to the 4 pixels, and I'm going to have 10 features that I want as my output. So I run this, and I have a 4 by 10 weight matrix. So now, when I take my 4 by 1 and multiply it by my 4 by 10, what's going to happen is 3224 gets multiplied by 2433. So 3 times 2 is 6, 2 times 4 is 8, 2 times 3 is 6, 4 times 3 is 12. But now, since I had this unit axis here that multiplies into 10 times, this unit vector, or I guess this single kind of column vector, gets broadcasted across all 10 of these columns. And this element-wise multiplication happens between 3224 and every one of these columns. So if we look at the last column here, 3 times 2 is 6, 2 times 4 is 8, 2 times 3 is 6, 4 times 4 is 16. So we could go through each one and we could see that we have basically kind of projected or copied virtually across all 10 columns our unit axis vector here. So that is our intermediate result, and what we want to do is we want to replicate our dot product, because as we saw in our initial implementation of matrix multiplications, the dot product occurs between the pixels and the weights. So the way we implement a dot product for all of our features is that we take the sum, and we take the sum across the row dimension. So across the row dimension means we're summing down. So 6 plus 8 is 14, plus 6 is 20, plus 12 is 32. So that's 32. 6 plus 6 is 12, plus 6 is 18, plus 8 is 26. So what we have effectively done is we've taken our first image pixels, and we've taken the dot product with all of the weights of our 10 features. But the way we've done it is that we've broadcasted our single column across all 10 features, and then we've taken the sum down the rows for each column to get our final 10 different dot products. So if we look at our shapes here, our A matrix has 5 images, 4 pixels. Our weight matrix has 4 weights, 1 for each pixel, and 10 output features. We instantiate our output matrix as before, still 5 by 10, except now all we have to do is we have to iterate through each row, broadcast it across the weights, take the sum, and we get our dot product. So we're taking the entire row of our matrix product, one row at a time, and we do that 5 times because we have 5 images, and we get this result here. So 32, 21, 27, 19, 34, 19, 36, 21, 26, 36. So we're doing one row with one operation. Whereas before, we would have had done 10 different operations to get 10 dot products. So that's the power of broadcasting in full display here. Okay, so I'm now going to go back to my matmul, and instead of my A and B being these toy examples, I'm going to use the actual MNIST examples, and I get the right answer, so it checks out. And then if I run this, it varies a bit, but I don't know why I'm not getting 150 or so, but close enough. So less than 200 microseconds. So if we go back up here, our Numba was 600 microseconds, which was faster than Python. PyTorch was faster than Python, but slower than Numba. So 600 microseconds for Numba. We're now down to 200 microseconds with PyTorch broadcasting. Okay, let's skip over here. And let's take a look at what this looks like visually. So if you look at the entire landscape, now I'm down to one for loop, right? So ultimately, we're trying to get rid of as many Python for loops as we can, because the Python for loops are the bottlenecks in our computation. So when we went from our naive implementation to our dot product implementation, we got rid of one for loop, and we had 2 left. Now that we've gone from our dot product implementation to our broadcasting implementation, we've gotten rid of another for loop. So now we only have 1 for loop left. So the only for loop is the one here, where we iterate across the images that we have in our data set. We add the unit axis, and I've kind of represented this unit axis by like making this vertical. And then in one fell swoop, so we take our unit axis, broadcasted, and this broadcasting happens during the operation. So it's not like we're copying it and then we're multiplying. But when we do this element-wise multiplication, our single vector of A gets broadcasted, gets copied virtually across the 10 features in our weight matrix. Every single one of these corresponding columns has a dot product performed between them, and that value gets stored in our output matrix. And then because we're doing 10 dot products, all 10 of these are going to get populated with one operation. Then we go down to image 2, and then the next 10 dot products, and then the next 10, and the next 10, the next 10. And that way, we only have 5 iterations that we go through, and we get our full 5 by 10 output matrix. And of course, just looking at here, we have our ith row of A broadcasted across our weight matrix. Take the sum down the columns, so across the row dimension, so vertically, and then we get our outputs. So that is broadcasting. That was at least in lesson 11 as far as we got. A couple more things. So I can now, because I have a much faster matmul operation, I can now do this on all of my 50,000 images for all of my weights. And now my output is 50,000 by 10, not 5 by 10. And this takes about 2 seconds, a little less than 2 seconds. So if you recall, our nested Python for loop was about 1 second for 5 images. This is now 50,000 images, and it's only, about twice that. So the last thing I wanted to do was I wanted to see if I could extend broadcasting to Numba, because we got such a speed boost when we compiled our dot product with Numba. What if we compiled broadcasting with Numba? So that's what we're going to do here. Here we have our matrices in NumPy array form. And now I'm going to compile with Numba my entire mapmul operation. And the reason I'm going to do that is because everything in here is now a NumPy operation. So NumPy a.shape, b.shape, NumPy.zeros, and then in NumPy we have the axis parameter for sum instead of the sum parameter or the dim parameter. So we have again our one for loop. Each image gets broadcasted across the entire weight matrix, and we take the sum down the columns to get our dot product, and that gets stored as that ith row in our output matrix. So I'm going to run that. Let's make sure it is correct, so it has the correct values as T1. So now we're going to time this, and now we're at 90 microseconds. So we were down to about 200 microseconds with broadcasting. Now we have that down to 90. And so now if we run our entire matmul for our entire training set, we are now less than the 1 second or 1.09 or 02 seconds it took to do 5 images. We can now do 50,000 images in half the time. So I was very excited that this worked. I wasn't really sure if it was going to work, but then as I was chipping away at it, I'm like, well, yeah, everything is pretty much the same in NumPy like we do in PyTorch, except here we're going to compile the entire operation instead of just compiling the broadcasting operation. And here we go. We went from 1 million microseconds down to 90. So 1.09 seconds to microseconds. And if we divide that by 90, so now we have about a 12,000x speed up from Python 3 nested loops to Numba compiled broadcasting. So that is it for this video. Again, I'm really excited, really relieved to be back in routine with the FASTAI Part 2 course, and expect a lot more videos and blog posts around that. And yeah, I will put the blog post description in the description below, and that has all the code that you see here plus some pros. And then I've also put a summary table that shows the timing comparisons across the different methods. So yeah, thanks again for watching, and I'll see you next time.